there, and welcome to the second lesson in this series, Introduction to Electronics. In our previous lesson, we showed that not all conductors behave in exactly the same way when a potential difference is applied across their ends. We showed that although a piece of copper wire and a piece of nichrome wire both obeyed Ohm's law, the resistance of each type of material was not the same. To explain these macroscopic observations, we introduced a model of what is happening at a microscopic level. In a metallic lattice, the energy levels of each atom combine to form bands of different energy. The energy band that contains the outer electrons is called the valence band. The unfilled energy levels also combine to form bands. The band closest to the valence band is called the conduction band. In metals, the valence band and conduction band overlap, making it possible for charges to move freely through metals when a small potential difference is applied to the ends of the conductor. This explains why metals are generally good conductors of electricity. We also showed that the overlap area is different in different types of metals, which explain why some are better conductors than others. In this lesson, we will investigate the effect of applying a potential difference to insulators, use energy band theory to explain our observations, and see how the properties of insulators can be used in electronic components called capacitors. By the end of this lesson, you should be able to use energy band theory to explain why insulators do not usually conduct electric current, describe how insulators are used in making a capacitor, and investigate the effect capacitors have on potential difference and on the current passing through a simple circuit. Just by looking at materials like plastic, polystyrene, paper, or wood, you can see that they are different to metals. But these materials not only look different, they also behave differently to metals when you apply a potential difference across their ends. Let's do a simple experiment similar to the one we did in the last lesson, but this time we'll test one of these non-metallic materials. Here I have a power supply connected in a circuit to an ammeter measuring on the 50 milliampere scale and a strip of plastic cut from a shopping bag. I've connected a voltmeter across the ends of the plastic strip. I'll increase the potential difference and see if the ammeter detects any readings of current. Here goes. I've set the power supply to 0,5 volts, but the ammeter shows no current. I'll increase the potential difference to 1 volt. Still no current. Let's increase the potential difference again and again. Still no current reading. I have increased the potential difference to a maximum using this power supply, but still cannot detect any current readings. So this plastic strip does not allow charges to flow through it. This material is clearly not a conductor and so is classified as an electrical insulator. To find out why insulators do not allow charges to move through them, even when a potential difference is applied to their ends, let's look at our energy band theory again. In an insulator, the atoms are usually non-metals. The valence electrons in non-metal atoms are closer to the nucleus of the atom than metals. When the non-metal atoms bond together to form giant molecules, they share electrons and fill the valence energy level of each atom. This type of chemical bonding results in a valence band in which the electrons are tightly held. In addition, the empty or unfilled energy levels of non-metal atoms that make up the conduction band are only found at higher energy levels further away from the nucleus in nonmetals than in metals. As a result, the conduction band formed in a giant molecule is separated from the valence band by an energy gap. Notice that these bands do not overlap as we found in metals. This means that the electrons in the valence band would need a lot of energy to move into the conduction band and cause the insulator to become a conductor. So when a small potential difference is applied across the ends of an insulator, no current passes through the insulator. It seems that to make an insulator become a conductor, we will need a much larger potential difference than this power supply can give us. Let's try a different piece of apparatus that you may have seen before. The Van der Graaf generator. When the Van der Graaf generator is turned on, a very large potential difference can be generated between the charged dome and this smaller earthed sphere. The only thing separating these two metal conductors is air. Air is made up of non-metallic gases and so is an insulator. Watch carefully what happens when I bring the earthed sphere close to the charged dome. Can you see there's a spark that flashes between the spheres? Electrons are accelerated from the small sphere through the air to the large positively charged sphere because of the very large potential difference between the two. Here, air is no longer an insulator, but a conductor. When an insulator acts as a conductor, we say that electrical breakdown occurs. Fortunately, electrical breakdown only happens when the potential difference and temperature are very high. During electrical breakdown, the electrons of an insulator, normally found tightly held in the valence band, gain enough energy to move across the energy gap and into the conduction band so that the insulator can act like a conductor. However, these electrons can't stay in the conduction band for very long. They return to the valence band and release the energy they gained in the form of heat or light. We see this release of energy as a spark. A good example of naturally occurring electrical breakdown is a lightning strike. Now, for the rest of this lesson, I want us to look at how insulators are used in a very important electronic component, the capacitor. Let's join Tate in the lab for this.
Hi everybody, today we're going to be investigating capacitors. A capacitor is an electronic component that is made from two conducting plates that are separated by a small gap. In some capacitors, the gap has air as the insulator. In some capacitors, a thin sheet of insulating material separates the conducting plates. The insulator in the capacitor is called a dielectric. Now, to show you what happens inside a capacitor, I will use these two metal plates inside the petri dish with some oil as the insulator. I've connected these two plates in series to the Van der Graaf generator. This plate is positively charged and this plate is negatively charged. You should recall that an electric field forms around any charged object. So between these two oppositely charged plates, we expect an electrical field to form. I want to demonstrate the effect this electric field has on small neutral objects, such as seeds, that are scattered in between the plates. Even though the seeds were neutral before I sprinkled them between the plates, they are affected by the electric field and become arranged in lines between the plates. To explain what has happened here, focus on the end of the seed that is closest to the positive plate. The large positive charge on the plates attracts electrons on the seed to this end, which then becomes negatively charged. As a result, the other end becomes positively charged. The electrons on the next seed are now attracted towards the positively charged end, and its other end becomes positively charged too. In this way, the seeds line up with the electric field formed between the plates. We say the neutral seeds have been polarized because they have temporary positive and negative ends. During this process, there is no flow of charge. The charge is blocked by the seeds and stored on the surface of the plate. In a capacitor, the molecules of a dielectric act like the seed and oil, preventing the flow of charge from the positive to the negative plates, even though there's a large potential difference between the plates. Since the charges on the plates cannot move, the capacitor is a charge storage device. The ratio between the amount of charge stored and the potential difference between the plates is called the capacitance, C of a capacitor. The SI unit of capacitance is a farad, named in honor of Michael Faraday. 1 farad is equal to 1 coulomb per volt. 1 farad is an extremely large value of capacitance. So, most capacitors are measured in microfarad. A microfarad is 1 times 10 to the minus 6 of a farad. Some capacitors are even measured in a smaller unit, the picofarad, which is 1 times 10 to the minus 12 of a farad. The capacitance of the capacitor is also related to the area of the plates, A, and the distance between the plates, D. What effect do you think the area will have on the capacitance? Well, a larger plate can store more charges, so the bigger the area of the plate, the larger the capacitance will be. We say the capacitance is directly proportional to the area of the plates, but it is inversely proportional to the distance between the plates. This means that when the distance between the plates is small, the capacitance is large, but when the distance between the plates is large, the capacitance decreases. Now, when the dielectric is air, the variables can be related in another special equation. C equals epsilon naught times A, the area of the plate, divided by D, the distance between the plates. Epsilon naught is a constant called the permittivity of space and is equal to 8,85 times 10 to the minus 12 farad per meter. Every different type of insulation material allows for different amounts of charge to be stored, dependent on their molecular makeup. So, each dielectric used has a particular constant, K, allocated to it. For air, this constant is equal to 1, but for other materials, the value is greater than 1. This means that the capacitance equation for air can be extended to include all dielectrics by adding the dielectric constant. C equals K times epsilon naught times A, the area of the plate, divided by D, the distance between the plates. Now, enough of all the theory. Let's see how a capacitor actually works in a simple circuit. In this circuit, I have a battery of two 1,5 volt cells connected in series. The battery is connected to a 1 farad capacitor, a 100 ohm resistor, and a special switch. When the switch is closed at the top, charge can flow from the battery into the capacitor and around the circuit. When the switch is closed at the bottom, the battery is disconnected. For this investigation, we will use the Explorer data logger connected to a current and a voltage sensor to see how the potential difference across the capacitor and the current passing through the circuits changes with time when the capacitor is charging and discharging. The data collected will be displayed as graphs shown on the laptop. Watch what happens when the switch is closed. Now the switch is opened and then placed in the discharge position. The top graph shows that the potential difference across the capacitor started from 0 volts and increased with time until it reached a maximum of 3 volts after about 60 seconds. When the switch was opened, the potential difference remained constant but decreased rapidly when the switch was closed. The second graph shows that the current started with a maximum value and decreased while the capacitor was charging.
but then increased when the capacitor discharged.
This investigation has showed us two very important characteristics of capacitors. Firstly, capacitors take a specific time to charge and discharge.
This property is useful in electronic circuits such as the ones you find in programmable washing machines or traffic lights. The time taken to charge and discharge a capacitor controls the time allocated for certain processes. Secondly, capacitors can store large quantities of charge. One example of where this property is useful is in the flash of a camera. When you press the button to take a picture using a flash, a capacitor discharges the energy it has stored. This results in a very bright, short flash of light as the energy is released into the circuit over a very short period of time.
Well, that's all I have to show you. Let's go to the studio and wrap up this lesson.
I hope you found Tate's explanations of how capacitors work as interesting as I did. You should keep in mind that capacitors are found in many electronic devices. One should never touch a capacitor, even if the power is turned off. The capacitor may still be charged, and releasing the stored charge in a very short time could give you a large shock. For your task today, I want you to investigate how connecting more than one capacitor in a circuit affects the overall potential difference across the circuit. A single 100 microfarad capacitor produced the following potential difference time graph. And the second line shows what happened when two identical capacitors were connected in parallel. What conclusions can you make about the effect of combining capacitors in parallel from these results? In our next lesson, we will consider the effect of current on semiconductors. See you then.
Yeah.